Title: Handling Device Heterogeneity for Deep Learning-Based Localization. The paper addresses the issue of device heterogeneity in deep learning-based localization systems, which affects the accuracy of cellular received signal strength (RSS) readings due to variations between different phone types. The authors propose several techniques to handle this problem, including traditional approaches and novel deep learning-based solutions. The traditional techniques include linear transformation, which assumes a linear relationship between RSS readings from different phones, and relative power technique, which uses ratios of RSS readings instead of absolute values. These methods have been used before with probabilistic models to solve device heterogeneity. The novel deep learning-based techniques leverage the universal learning ability of deep models to solve the heterogeneity problem. The first technique involves transferring knowledge gained by training a deep model on one device to other devices through fine-tuning using a few samples for the tuning devices. The second technique models the heterogeneity problem as a multitask learning problem, where the model is trained on data from multiple devices simultaneously. The authors implemented and evaluated these techniques in a proposed framework on different Android phones across 4 testbeds. The results showed that the proposed techniques can improve localization accuracy by more than 220% compared to systems without heterogeneity handling. In conclusion, the paper presents a comprehensive approach to addressing device heterogeneity in deep learning-based localization systems, offering both traditional and novel deep learning-based solutions that significantly improve localization accuracy. Here is a combined summary of pages 3 and 4 of the research paper. Handling device heterogeneity is crucial for deep learning-based localization. 3 techniques are proposed to address this issue: power ratio, power difference, and deep learning-based techniques. The power ratio technique transforms RSS values to relative power, while the power difference technique takes the difference between RSS values. Deep learning-based techniques, including transfer learning and multitask learning, are employed to automatically figure out the relation between RSS values coming from different cell towers. Transfer learning allows reusing a model pre-trained using a large number of samples from a master device as a starting point for fine-tuning the model for another device. This technique requires only a few samples for tuning a new device. The model structure consists of common feature extraction layers, preprocessed features, and an output layer. The network is trained using a large dataset from the master device, and then the output layer weights are tuned using a few samples from the new device. Multitask learning is a direct extension of transfer learning when the number of training samples from the slave device approaches the number of samples from the master device. This technique solves the heterogeneity problem as a multitask learning problem through learning the mapping between RSS and locations from different devices simultaneously. The model is trained with samples from different devices, allowing it to generalize for heterogeneous devices. The performance of the proposed heterogeneity handling techniques is evaluated using a test bed covering 0.2 square kilometers in an urban area and 1.2 square kilometers in a rural area in Alexandria, Egypt. Cellular data and GPS ground truth locations are collected by drivers using different devices. The results show that all heterogeneity handling techniques improve the system accuracy compared to a system that does not handle device differences. The deep learning heterogeneity handling techniques are superior to other techniques, with the multitask learning technique achieving a median localization accuracy of 24 meters, 22 meters, 29 meters, and 26 meters in 4 experiments, respectively. This is an enhancement of 220.8%, 286.3%, 1051%, and 1176% in median error compared to training without handling heterogeneity. Here is the combined summary. The paper investigates techniques for addressing device heterogeneity in deep cellular localization systems, where different devices have varying hardware and software capabilities. The proposed solutions focus on either approximating a function that maps features from one device to another or sharing knowledge across different devices. 4 independent test beds are used to evaluate the impact of each device heterogeneity handling technique on the deep model's localization accuracy. The results, shown in Figure 4, demonstrate that sharing knowledge across devices can improve localization accuracy by more than 220%. This is achieved through transfer learning, which enables the model to learn from one device and apply that knowledge to another. The table summarizes the localization results, showing the 25th, 50th, and 75th percentiles of the localization error for each experiment. The paper highlights the significance of handling device heterogeneity in deep learning-based localization systems, as it can lead to improved accuracy and robustness. The proposed techniques, including linear transformation, power difference, power ratio, and multitask learning, are compared to a baseline model without heterogeneity handling. The results demonstrate that these techniques can mitigate the effects of device heterogeneity, leading to more accurate and reliable localization. The paper concludes by emphasizing the importance of addressing device heterogeneity in deep cellular localization systems and highlighting the potential of transfer learning as a solution. The references provided demonstrate the breadth of research in this area, including works on multitask learning, ad hoc networks, and quantum computing for location determination.